This is Ideas Worth Exploring by Mark MacDonald. When the ancient Egyptians made a mummy, they would take out each of the organs and carefully store them in jars, preserved and ready for when the deceased person might need them again. Except for the brain. The brain was pulled out through the nose using a hook, and then thrown away because they thought it was a useless waste of space. Aristotle believed that the brain was a radiator that kept your blood cool and made sure your heart didn't overheat. Yeah, eventually we figured out that the brain is kind of important and that it's the thing in charge of your thoughts and memories and movement and speech, etc., etc. So we've learned some things since the time of the Egyptian mummy brain hooks, like how brains used electricity to send signals. Early experiments with electricity and the nervous system were a big part of why Mary Shelley thought that Dr. Frankenstein could create life by electrifying a corpse. We've also learned how different parts of the brain have different functions, which is illustrated by the story of Phineas Gage, who had an iron rod go through his brain, but he was still able to walk and talk afterwards and lived for another 12 years. And we've also learned that brains are made of cells called neurons, which work together to generate our memories and thoughts. This is the first of a two-part series about brains. This first part is all about brain cells, what they look like and how they do the electricity thing, and then a brief dip into something called a neural network. In the next part, I'll talk about how our brains store memories, some common brain misconceptions, and some tricks you can use to be a better rememberer. Okay, time to jump into it. I will now proceed to uncover the mysteries of consciousness. Wait, I don't know how to do that. Okay, instead, how about I tell you what a brain is made of? A human adult brain weighs about 3 pounds, as much as a toaster or 3 pounds of butter. It looks like a pinkish-gray blob covered in wrinkles and folds. But if you zoom in, way in, you see individual cells that look like alien starfish snakes. The neurons. Neurons are brain cells. Your brain is made of almost 100 billion of them. Remember that a cell is the tiniest part of you that could survive on its own if you kept it fed and watered. You aren't just you, you're billions and billions of tiny little cells that work together to make a human, and the brain and nerve cells are called neurons. The goal for today is to understand the parts of a neuron and how they send messages to each other and the rest of the body. Which side of the brain has the most neurons? The inside. Where are neurons kept when they commit a crime? A brain cell. What do you call two neurons in jail? Cellmates. What do neurons use to talk to each other? Cell phones. Favorite vegetable? Celery. Okay, I'm done. You know how I said that neurons look like alien starfish snakes? Well, I'm going to amend that. They actually look like alien tree root worms. A neuron has a cell body, with what looks like roots coming out of it. The roots are called dendrites, and they receive chemical signals from other neurons. Dendrites branch out in all directions, so a neuron can connect to as many other neurons as it needs to and receive signals from them. Dendrites are the brain cell's receivers. But if you think that dendrites also send out signals as well as receive them, you would be wrong. That's the job of the next vocabulary word. The neuron also has a long worm-like arm sticking out of it, which is named the axon. An axon is also called a nerve fiber. Oh, by the way, neurons aren't only brain cells, they're also your nerve cells. They're the same thing. Actually, when I hear the word nerve, I usually picture something long and dangly, like an axon. Axons let the neurons send electrical signals over long distances, kind of like a telephone cable. So dendrites are the tree root-like receivers, while the axon is the telephone cable-like transmitter. So that's what a neuron looks like. Now, what does it do? Math. The fundamental brain units need to be able to do two things. They need to be able to add, and they need to be able to send the result of that addition onto the other neurons. It managed to do both of these things using only chemistry and physics. Let's start with the physics of adding. If you were physics, how would you invent the concept of addition? It's actually pretty easy. You just need something to represent numbers and a check to see what the total is. Brains use electric charges for numbers, and to check the result, they use voltage-gated ion channels. But first, some background. Neurons add using electric charges in the form of ions, or charged atoms. Ions include things like sodium and chloride, the two components of table salt. Yes, you have salt in your brain, and also everywhere else in your body. The ions and salt are essential for cells to function. Sodium has a positive charge. So do other minerals like calcium and magnesium. Chloride has a negative charge. So do other things that I won't bother to mention right now. Moving ions around can create a sort of electric pressure called voltage. If positive ions go into the cell, the voltage will go up. If positive ions go out, voltage goes down. Same with negative ions, but reversed. So your brain is salty, and the salt ions are the numbers your brain uses to add. A neuron gets signals from other neurons it's touching, and those signals get turned into ions flowing into and out of the cell. More on that in a minute. The ions create a voltage inside the neuron, and the total voltage is the sum of adding up the contributions from all the ions that flowed into and out of it. So that's the first part of how a neuron adds, using ions as numbers and voltage as the total. But how does the cell check what the total is? With a roller coaster. A neuron starts out at a negative voltage, more positive outside than inside, but signals from other neurons allow positive charges to enter the cell. This makes the voltage go up, and when the voltage reaches a threshold, it opens channels in the cell membrane that are sensitive to voltage, voltage-gated ion channels. This lets positive ions rush in and raises the voltage really quickly in what's called an action potential, or, as I prefer to call it, a voltage-gated ion channel roller coaster ride. So once the voltage gets up to a lower threshold, the channels open, a bunch of positive ions flow in, and the voltage goes way up until it reaches an upper threshold. Then the first channels close and another set opens, a bunch of positive ions flow out, and the voltage goes down. Then those channels close and their cousins, the ion pumps, work to get the voltage back to its pre-roller coaster level. So up, back down, then stabilize. This creates a very clear yes-no signal that's hard to mistake. Either a neuron fires an action potential or it doesn't, and it sends this signal to the next neurons along. It's important that this signal is so clear and obvious because you don't really want your brain signals to get lost or misread. So neurons can add by building up voltage to a certain threshold, then sending out a signal and resetting the voltage once it reaches that threshold. It's like a person who doesn't know any numbers except 10, but he can count on his fingers, and when all the fingers are up, he knows it's 10. So he yells 10 and then starts counting again from 0. Except instead of a person, it's just physics and chemistry doing the adding. It's really kind of neat. By the way, we learned about action potentials by studying the giant axon of a squid, which can be up to 1 millimeter in diameter and is visible to the naked eye. Okay, we've learned how neurons can count and then signal when they reach a threshold. But to prepare you for the next episode, there are a few more things you need to know. Those are some more about axons, then neurotransmitters and synapses, and finally myelin sheaths. So a neuron can create an action potential roller coaster on a section of its cell membrane. In addition to making a very clear yes-no signal, the action potential also helps the signal travel long distances. Remember the axon, the neuron's long telephone cable it uses to transmit a signal over distance? Axons can be very long. In the human body, the longest one goes from your foot all the way to the base of your spinal column, over 1 meter long. That's just for a single cell. Most of them are smaller, think millimeters, but that's still a long distance for a microscopic cell. The action potential helps the electric signal travel over that long distance. That's because as soon as the action potential occurs on one section of the membrane and the voltage rises, the ions spread out and push the voltage on nearby parts of the membrane up past the threshold and make them ride the roller coaster too. And this happens all the way down to the end of the axon, where the action potential causes the cell to release neurotransmitters to signal to the next neurons along. Oh, I haven't explained neurotransmitters yet. Neurotransmitters are chemicals that neurons use to talk to each other. In general, each neuron only has a single type of neurotransmitter, though some can use 2 or more. We can connect some neurotransmitters to specific purposes, like serotonin is used by the parts of the brain that regulate your mood, behavior, sleep, and memory. Adrenaline is associated with stress and helps your brain make quick decisions. And endorphins inhibit pain and create feelings of pleasure. Do you know that dentists keep fish in their office because they have a calming effect on patients? It's because of all the endorphins. So here's how neurotransmitters work. When an action potential reaches the end of a neuron, the increased voltage causes little pouches of neurotransmitters to fuse with the membrane of the neuron and release their cargo into the wild. The neurotransmitters then diffuse across a small gap called a synapse to the other neuron. The neurotransmitters activate channels in the neuron's cell membrane that lets ions in or out of and change the voltage inside. So to repeat, it goes neurotransmitters, membrane channels, ions flowing in and out. And then the neuron does math. So now you know the full story, from neurotransmitters to voltage buildup to action potential and back to neurotransmitters. And yes, it is a little more complicated than that. There are lots of little quirks I didn't mention, but now you know all the most important parts of how neurons work. 2 more things about neurons. First, if you didn't catch it, the place where one neuron meets with another is called a synapse, and that will be important in the next episode. That's because, in a way, the total computing power of your brain is proportional to the number of synapses it can form. What's a neuron's favorite cookie? Ginger snaps. Finally, the myelin sheath. Animals with backbones, frogs and fish and humans, for example, have found a way to upgrade some of their neurons to make electrical signals travel faster. This upgrade is in the form of a bunch of little insulating blankets wrapped around the axon at intervals along its length. These blankets are made of a fatty substance called myelin. You know what gets on my nerves? Myelin. A myelin sheath surrounds an axon and insulates it in a way that lets electrical signals travel much faster by reducing the capacitance and increasing the resistance across the membrane. Don't worry too much about what that means, just be happy that it works. Basically, what you need to know here is that myelin makes signals go faster, and the thicker the myelin, the better. Here's the comparison. The signal in a small axon without a myelin sheath can travel about 3 miles per hour, about as fast as the average walking pace. These slow signals are often from pain receptors. A larger axon covered in a myelin sheath can have signals that travel over 250 miles per hour. These fast signals are often for things like your sense of touch. But even that's nothing compared to an electrical signal sent through a wire, which can get close to the speed of light, 10 million times faster than your brain signals. So robots have the advantage over us there, and there's not much we can do about it. That's it for neurons. Now you know what they look like and how they send signals. But sadly, brains are still very mysterious. Just knowing about the neurons that form the building blocks of a brain hasn't really gotten us much closer to understanding how pattern recognition and thinking work. Unless, have you ever heard of a computer algorithm called a neural network? I won't go into the details here, but learning how brains work inspired computer scientists to try to program machines in the same way, with a set of digital neurons that pass along signals to each other. We use neural networks all the time. They're what our phones use for voice recognition, image filters, predictive text, Google Translate, ChatGPT, and a whole bunch of other things. Neural networks are the most common form of artificial intelligence, which is going to become more and more important over the next few years. Neural networks are an amazing technology that demonstrates that basic tasks such as recognizing patterns and sorting things into categories, which are parts of what we usually think of as thinking, can be done by anything as long as it has the ability to add and send a signal onward, be it transistors in a computer or neurons in a brain, or humans pretending to be neurons. I want to point you to a YouTube video called The Stillwell Brain by YouTuber Vsauce, who built a neural network with humans as the neurons, where each human raised a flag to signal an action potential. And it worked. The people brain was successful at looking at a set of pixels and interpreting it as a number. So neurons really can be made of anything. And if you really want to understand how thinking works, a neural network might be a place to start. Neural networks are a great demonstration of how science happens. First, we notice how neurons in our brain work and see there's lots of complexity with gushy chemical neurotransmitters and messy action potentials. Then we try to cut away that complexity and see what the minimum requirements are to create something that perceives and learns. Then, once we succeed, we use that new knowledge to create products that are useful to society, like Snapchat filters that give you dog ears. What do neuroscientists say when they direct a movie? Lights, camera, action. Why was the neuron sad? Because he got fired. Well, that's it. Neurons are brain cells that have dendrites to receive signals and an axon to carry a signal away. Where two brain cells meet is called a synapse, and that's where neurons send neurotransmitters to each other. Neurons build up ions from the signals they get, and when the voltage reaches a certain threshold, they fire an action potential that sends an electrical signal down the axon to communicate with other neurons. A myelin sheath makes the signal travel faster, and the thicker the myelin, the better. And finally, a bunch of neurons that work together can be called a neural network, but we usually use that term instead for a computer algorithm inspired by how our brains work that allows your phone to be smarter than you. The end. Come back next time for a discussion of how neurons can store memories and how you, yes you, can be a better rememberer. Peace. This has been Ideas Worth Exploring by Mark McDonald.